5.4 Hess's law of additivity of reaction and enthalpies. Okay, let's see what is this. As you see, a reaction might not be just one stage or one reaction. To get to a product, there might be multiple reaction happening. Looking at that, first the reactant is N2NO2. They react, produce NO. And after that, NO will decay into, will react with oxygen to give NO2. So it's just a two reaction. Now we want to see what is the Hess's law. The value of the delta H for any reaction that can be written in steps equal to sum of the value of the enthalpies for each of the individual steps. Is there like that? There's a two-step reaction. The overall, the enthalpy change is going to be addition of these enthalpies. For example, overall enthalpies is when N2O2 getting to NO2, right? The initial going to final. The difference between the enthalpy of the initial and final is plus 34. Let's say we don't have that. We have just steps. From here to here is the first step. From here to here is the second step. If you add 90 to negative 56, you need to get, you will get positive 34. So overall enthalpy of a reaction is equivalent to the addition of the enthalpies of each stages. Okay. Now here is what we say, the delta H of target is the addition of the delta H of each steps. Let's look at this question to understand that better. So the target equation is N2 plus O2 give you 2NO. You want to find that, but just we know the steps. It's two reaction happening. The first is half N2 plus O2 give you NO2, the delta H is given. And NO plus 1 over 2O2 give you NO2. So I need to rearrange it in such a way that if I add them, I will get the target. So this is how we do it. See, N2 is on right side. Here, N2, I see it on one place and it is right side. So it's in the correct side, but the coefficient here is 1, but here is 2. I need to do something about it. That's why I multiply this one by 2. When I multiply this one by 2, is you have to multiply everything by 2, even your delta H. So multiply by 2, it becomes N2. You have a 2 here and you have a 2 here. As you see, this step is done there. You need to multiply your delta H by 2. So it's good. Now look at that. NO is on the right side, but I have NO in a second reaction. Oh, I have NO on the left, so it's the side is wrong. That's why I need to switch it. To switch it means you have to really multiply everything by negative. Also, the coefficient here is 2, but the coefficient here is 1, so I have to multiply 2 as well. So multiplying that by negative 2 means the side will be switched. So NO2 will come here, as you see. You have to multiply by 2 as well. NO going to the other side, you multiply by 2, and 1 over 2 multiplied by 2 is going to be 1, as you see here. Also, the delta H here need to be multiplied by negative 2. And it's done here. So we have that. You need to check if you have done it correctly. See, 2NO, NO2 here, and here is 2NO2. So they cancel. If you add them, they're on the different side, they cancel. Then I have N2 plus 2O2 just on the right side. See, I have N2 and O2 here. And 2N, oh, here, guys, I have 2O2 here, right? And 1O2 here. So basically, this will go away, and you just have O2, 1O2 there. N2 plus O2 give you 2NO, as you have there. Basically, you add the right side. If you don't like that way, you add the right side, you add the left side, as is done here, and 2O2, 2NO2, so it's here, and add all of this left side, these three things there, then you can cancel. Now we have 2O2 here, 1O2, so cancel, this become 1, and this is the net or target is achieved. Now we know what, we know it, we did it right. So when it's right, so you just simply add the delta H's there to get the delta H of the target. This is the Hess law. This is another example. What is the enthalpy change for the formation of 1 mole of the butane? So here is the butane, here is a target equation. The step is given to you, we need to figure it out. So we look at C4H10. C4H10 is here and is the wrong side, should be at the other side, right? That's why we need to multiply it by -1. Everything will be switched. The coefficient is right, so it's 1 and 1 here. We don't have to touch the coefficient. Look at the hydrogen. See, the hydrogen is here as one place, and it's the coefficient of that is 5, but the coefficient is 2. What should I do? I need to multiply it by 5/2, because 5/2 multiplied by 2 is 5, and I get that. I need to do it to all of that, multiply that by 5/2, everything. And is in a left side, or is in the left side, I don't need to put any negative things. C here, I have C here. The coefficient of the is on the left side, is on the left side. The coefficient is 4, so I need to multiply by 4. Means I need to multiply everything by 4. If I apply that negative, so everything here will be switched, as you see. Is multiplied by 4, everything in here is 5/2. This is what we have. You add up the left side, that's it. We have, you add up the right side, this is what we have. We cancel the things. See, 5H2 and 5H2 cancel. 4CO is 4CO2 cancel, and oxygen is canceled with oxygen. This is what left. This is my target. Look, this is my target. Then you need to add the delta H. The delta H you add there, it will give you the delta H of the target. There is another example. Determine the enthalpy change involving the formation of the 2 moles of the liquid propanol. So I'm just looking at C. C is here. The coefficient is 6, means they are both in the left side, so I just need to multiply everything by 6 here. Looking at C3H7OH, so it's on the right side, right here, left side. I need to multiply by negative, but there is 2 coefficients. I need to have 2 coefficients, so I multiply everything by -2 as done. And hydrogen is here, the coefficient is 8. On the right side, I just multiply that by 8. So we do that, we add them, we cancel things, we get our target, and we add all of the delta H, and this is what we have. So for practice, do question 1, 2, 3. This is on page 3 to 7. Now, multi-step energy calculation. So we know that the heat flow is Q is MC delta T. We had enthalpy change delta H is equal to N multiplied by the molar enthalpy, and Hess's law that we did, right? So guys, this is the 3 things we did discuss before. Now looking at this question, okay. In this process of production of sodium carbonate, as one step is determining the composition of sodium hydrogen carbonate. What quantity of chemical energy delta H is required to decompose 100 kilograms of the sodium hydrogen carbonate, right? So knowing this is the enthalpy change for this reaction is what? Is 129. I want to see for sodium hydrogen carbonate, so NaHCO3, 2 mole of that will produce that. Let's just look at the molar enthalpy. Since for 2 mole, this energy will be released, I want to see for 1 mole or molar enthalpy. Knowing that delta H is N delta HR, so molar enthalpy is equal to the delta H divided by N. Here the N is 2, because for 2 mole, this energy is released. This will give you energy released by 1 mole. Now for 100 kilogram, I need to see how many mole it is. Convert this one, mole is gram divided by the molar mass. This give you 1.19 kilomole. Again, delta H is N delta H, the molar enthalpy we calculated before, and we got it here. So we do it and we find the molar enthalpy, the enthalpy released by 100 kilogram. Here is another example. How much energy can be obtained from roasting 50 kilogram of zinc sulfide ores? First, this is a target. We need to find the enthalpy of that using the Hess's law. So looking at ZNS is here on the right side. Don't need to do anything to fix it. That's just multiplied by 1 means we don't need to do anything to that. It's the right side, doing right things. Oxygen, we have oxygen on 2 places. That's why it's not a good idea to think about oxygen. Just find something that is just appear one time. ZNO is here. I don't have ZNO in other places. It's good. So is in the wrong place. I have to multiply this one by -1. So I'm fixing that. The last one, the first one. And SO2 is here, is on the right side, right coefficient. So I don't need to do anything. It's just multiplied by 1. So I'm doing it. Of course, make sure that you do the changes to the delta H as well. You add them up, you get the target. So it's good that you add your delta H to get the delta H of this reaction. So knowing that 50 kilogram, you convert it to the mole. So this is kind of molar enthalpy because 1 mole of ZNS will produce that many energy, that much energy. So have molar enthalpy, the mole you find it, multiply by delta H is equal, and multiply by the molar enthalpy, we'll get the delta H released by 50 kilogram, like that. Do practice, do question 4 and 5. This is page 329.